Well, 240,000 miles away, a rock hangs in the sky that we could reach in 3 days, 44 million miles away. On a good day, when the orbits line up just right, sits a rusted, frozen desert that would take us 7 months to reach one way, with no way to turn back if something goes wrong halfway there. One of these places has no air, no weather, and temperature swings of over 500 degrees Fahrenheit between day and night. Other one has an atmosphere so thin it might as well not exist, dust storms that can swallow the entire planet for months at a time, and a gravity so weak your bones would start dissolving the moment you unpacked your bags. Neither of these places wants us there. Neither of these places was built for anything alive. And yet, right now, in boardrooms in Texas, in laboratories outside Tokyo, in government facilities in Beijing and Bangalore, some of the smartest engineers alive are running the numbers on which of these two dead worlds we should try to live on first. This isn't a hypothetical anymore. This is a question with $1 trillion answer attached to it. And depending on who you ask, NASA, SpaceX, China's National Space Administration, or European Space Agency, you'll get a different answer every single time. So which is it? Do we go back to the moon, the place we already visited 50 years ago and never really finished exploring? Or do we leap straight for Mars, the only other rocky world in the solar system that even remotely resembles Earth? Consider for a moment, what's actually at stake in getting this decision wrong? Every kilogram sent to either world costs, even with today's dramatically cheaper reusable rockets, thousands of dollars. Every habitat design decision, every choice of power source, every material selected for radiation shielding, locks in years of downstream engineering and cost once construction actually begins. And every human being who eventually lives, works, and potentially raises a family on either world is trusting their survival to decisions being debated right now by engineers who are working with genuinely incomplete data on some of the most fundamental questions involved, like whether the human body can even function normally after a decade under partial gravity. By the end of this video, you're going to understand exactly why this question is so much harder than it looks, and exactly why the answer might not be the one you're expecting. Let's break it down. If you're new here, welcome. This channel exists for exactly one reason: to take the biggest, strangest, most consequential questions about our future in space and actually walk through them properly. Not with hype, not with Hollywood nonsense, but with the real numbers, the real engineering constraints, and the real trade-offs that the people actually building this future are wrestling with right now. And there is no bigger question in space right now than this one. Here's the thing that a lot of space content on this platform gets wrong. They treat this like a personality contest. Mars is cool because it's red and mysterious and has been in 100 science fiction movies. Moon is boring because we already went there, planted a flag, and came home. Let's strip away the marketing, strip away the vibes, and what you're left with is an engineering problem of staggering complexity where every single decision, how far away it is, how strong the gravity is, what the ground is made of, how cold it gets at night, has a cascading effect on human survival that most people never stop to think about. This video is going to walk through every major category where these two worlds go head to head: distance and accessibility, gravity and the human body, radiation exposure, water and resources, feeding a colony, temperature and weather, building materials and construction, who's actually in charge and who owns any of it, communication and isolation, economics and funding reality, the actual global race happening right now, honest objections to everything you're about to hear, and finally, the verdict this whole video has been building toward. At the end, we're going to give you an actual answer, not a wishy-washy, well, it depends. A real conclusion, built category by category from the evidence. But I'll warn you now, the answer is not going to be as simple as Moon good, Mars bad, or Mars good, Moon bad. Well, the real answer is stranger, and honestly more interesting than that. Stick around, because the case is going to flip more than once before we get there. Before we get into the hard numbers, it's worth understanding how we actually got to a point where this question is even being seriously asked with real budgets attached, because this debate wouldn't appear out of nowhere. A brief history of this debate, humanity's first real answer to Moon or Mars, came during Cold War. And it wasn't really a debate at all. It was a race, and the destination was never in question. Moon was chosen for the Apollo program not primarily for its scientific value, though there was plenty of that too, but because it was the most dramatic, most achieved, most visibly demonstrable target available with 1960s technology, a target close enough to actually reach within a single presidential decade, as President Kennedy explicitly framed it in his famous 1962 Rice University speech, where he stated the goal of landing on the moon within the decade specifically because it was hard, not because it was easy. Between 1969 and 1972, 12 American astronauts walked on the lunar surface across 6 successful landing missions. And then, almost as abruptly as it began, crewed lunar exploration simply stopped. No human being has set foot on the moon since Apollo 17's Gene Cernan and Harrison Schmitt left the lunar surface in December of 1997. Reasons were overwhelmingly political and financial rather than technical. Once the Cold War's symbolic space race had been definitively won, public and congressional appetite for the enormous cost of continued lunar missions evaporated quickly, and NASA's budget as a percentage of total federal spending, which had peaked over 4% in the mid-1960s, collapsed to under 1% within a few years and has stayed there ever since. For the following few decades, robotic exploration quietly took over as the primary way humanity actually studied both worlds. The moon received comparatively less attention through the 1980s and 1990s, while Mars increasingly became the focus of ambitious robotic missions. Viking 1 and 2 in the 1970s, Pathfinder and its small Sojourner rover in 1997, and then the genuinely spectacular twin rover missions Spirit and Opportunity in 2004, which were designed for a 90-day mission and ended up operating for years in Opportunity's case, until that 2018 dust storm we discussed earlier finally ended it after nearly 15 years on the Martian surface. Well, this sustained, highly publicized robotic success on Mars, combined with the cultural and cinematic mystique the Red Planet had already accumulated through decades of science fiction, quietly shifted public imagination toward Mars as the next real destination for humanity, even while the moon sat comparatively neglected in the public conversation for the better part of 3 decades. A scientific case for returning to the moon experienced a genuine renaissance starting in the 2000s and accelerating sharply through the 2010s and 2020s. Driven almost entirely by the discovery of polar water ice we covered back in Chapter 4. That single discovery transformed the moon from what many considered a been there, done that destination into a genuinely valuable strategic asset, a place with real, extractable resources rather than just historical significance. And this discovery is arguably the single biggest reason the moon has clawed its way back to the center of near-term space policy after decades on the sidelines. At the same time, the 2010s saw the rise of a genuinely new force in this entire debate. Private spaceflight companies, and specifically SpaceX, whose founder Elon Musk had explicitly and publicly stated Mars colonization as his company's founding, driving purpose since well before the company achieved its first successful orbital launch. This is a genuinely unusual dynamic in the history of space exploration, a private company with founder-driven Mars ambitions operating in parallel with, and sometimes in conjunction with, national space agencies whose own roadmaps have prioritized the moon first. NASA itself, through its official long-term strategy, has attempted to reconcile these two tracks by adopting the moon to Mars framing explicitly, positioning lunar exploration not as a competitor to Mars ambitions but as the necessary, sequential predecessor to them, a framing that, as we've walked through across this entire video, holds up remarkably well once you actually dig into the engineering and economic details category by category. So when you hear this debate framed today as Mars versus the moon, what you're actually hearing is the echo of 2 different historical momentums colliding. Government-led, resource-driven return to the moon that re-accelerated dramatically after the 2009 ice discovery, and a private sector-led, founder-driven Mars ambition that predates that discovery and has continued to run on its own separate track ever since. Understanding that these are 2 different historical threads, rather than a single continuous debate, helps explain why the 2 sides of this argument often talk past each other so completely online. They're not actually disagreeing about the same set of facts, they're often responding to entirely different underlying motivations for going to space in the first place. With that context in mind, let's get into the actual numbers. The distance problem. Let's start with raw numbers, because distance is the variable that touches every single other variable on this list. It affects cost. It affects risk. It affects how fast you can fix a mistake. It affects whether astronauts can go home if something goes catastrophically wrong. The moon sits at an average distance of about 238,855 miles from Earth. NASA's Apollo missions made the trip in roughly 3 days. Artemis program, using the new Orion spacecraft, is targeting a similar window, somewhere between 2.5 and 4 days depending on the trajectory. On space travel terms, the moon is basically next door. It's a weekend road trip. Well, you could leave Florida on a Friday and, in Apollo-era terms, be walking on lunar regolith by Monday morning. Mars is an entirely different universe of a problem. Because Mars and Earth are both orbiting the Sun at different speeds and different distances, the gap between them is constantly changing. At its closest, during what's called opposition, Mars can be as near as about 33.9 million miles away. At its farthest, when the two planets are on opposite sides of the Sun, that distance balloons to over 250 million miles. But here's the part most people miss. You can't just fly to Mars whenever it happens to be closest. Spacecraft don't travel in straight lines. They travel along curved paths called transfer orbits, using the least amount of fuel possible to reach a moving target while the spacecraft itself is also moving. The most fuel-efficient path, called a Hohmann transfer orbit, takes advantage of a launch window that only opens once every 26 months, when Earth and Mars align in just the right way. Miss that window, and you wait over 2 years for the next one. Using this most efficient trajectory, a one-way trip to Mars takes somewhere between 6 and 9 months. NASA's own mission planning documents typically use a figure of around 7 months, roughly 210 days, as the baseline. While some faster trajectories using more fuel could theoretically shave that down to 4 or 5 months, but they cost dramatically more propellant that has to be carried, at enormous expense, out of Earth's gravity well in the first place. Let that sink in for a second. A trip to the moon, 3 days. A trip to Mars, 7 months. That's not a difference of degree, that's a difference of kind. And it's not just about how long the crew spends cooped up in a metal tube, though that matters too, which we'll get to later. It's about what happens when something breaks. During Apollo 13, in April of 1970, an oxygen tank exploded roughly 200,000 miles from Earth, about 56 hours into the mist. Ion. Mission control in Houston had communication delays measured in about a second and a half round trip. Engineers on the ground could diagnose the problem, run simulations, test procedures on a duplicate spacecraft, and radio instructions to the crew in near real time. Astronauts were home within 4 days of the accident. Now imagine the same kind of accident happening to a Mars-bound crew 4 months into a 7-month transit. Communication delay at that distance can range from about 4 minutes to over 20 minutes each way, depending on the relative positions of Earth and Mars, meaning a simple back and forth exchange with mission control could take 40 minutes just for one round trip. And even with instructions in hand, there is no turning around and coming home in 4 days. There is no rescue mission. There is no abort. Whatever is broken, the crew has to fix it themselves with whatever's on board, because the nearest human being with an alternative solution is tens of millions of miles away. A single fact: the survivability of failure might be the single most underrated variable in this entire debate. On the moon, a critical habitat failure could realistically see a rescue or resupply mission arrive within days. On Mars, in the worst-case timing, a crisis discovered right after a launch window closes could mean waiting over 2 years for the next resupply opportunity to even physically arrive. On pure accessibility, this one isn't close. The moon wins by an enormous margin. It's closer, it is faster to reach, it is far easier to resupply, and it is dramatically safer in the event of an emergency. But distance isn't destiny. Just because somewhere is easy to reach doesn't mean it's a good place to actually live. And this is where things start getting a lot more complicated, because the moment you land, gravity takes over. Degravity problem. Here's a fact that surprises a lot of people. The moon and Mars do not have the same gravity, not even close. Earth's surface gravity is our baseline, 1g. The moon's gravity is about 0.166 g, roughly 1/6 of Earth's. Mars sits at about 0.38 g, a little more than 1/3 of Earth's. At first glance, that might sound like a win for Mars. More gravity is more Earth-like, right? Closer to what our bodies evolved for over hundreds of thousands of years. That instinct is correct, but it's not nearly enough on its own. And this is one of the most sobering scientific problems in the entire colonization debate, because we genuinely do not know if either amount is survivable for human beings long term. Almost everything we know about the effects of reduced gravity on the human body comes from one place, the International Space Station in microgravity, which is essentially zero-G. Astronauts who spend 6 months to a year aboard the ISS experience measurable, sometimes severe physiological effects. Bone density loss of roughly 1 to 2% per month in weight-bearing bones like the hips and spine, while a significant muscle atrophy, particularly in the legs and back, cardiovascular deconditioning, because the heart no longer has to work against gravity to pump blood throughout the body. It shifts toward the head that can cause vision problems, a condition NASA now calls spaceflight-associated neuroocular syndrome, which in some astronauts has caused lasting changes to eye structure, immune system dysregulation. And that's before you even get to the psychological toll of isolation and confinement, which we'll come back to later. A problem is that zero-G research doesn't map cleanly onto 166G, or 38G. Nobody has ever kept a human being at lunar or Martian gravity for an extended period because we simply don't have the infrastructure to test it. We don't have rotating gravity labs in orbit. We don't have long-duration lunar or Martian habitats yet. Every model of what partial gravity does to the human body over years or decades is, right now, an educated guess extrapolated from full gravity and zero-gravity data points, with nothing in between. This is genuinely one of the biggest open questions in all of human spaceflight, and it deserves far more attention than it usually gets in space content on this platform. While some researchers believe that even partial gravity, as low as the moon's 1/6, will be enough to meaningfully slow bone and muscle loss compared to full microgravity, especially when combined with resistance exercise. Others are far less optimistic, pointing out that the difference between 1/6 gravity and zero gravity might be smaller than we'd like to believe. In terms of the biological signal, the body actually needs to maintain bone density. Mars, at over a third of Earth's gravity, is a meaningfully stronger signal than the moon's 1/6. Colonists would likely still experience some bone and muscle loss over time, but most physiologists expect it to be substantially less severe than either lunar or zero gravity. This matters enormously for a genuine, permanent, multi-generational colony, because a colony isn't just about surviving a mission and coming home. It's about people living, working, and potentially raising children in that environment for their entire lives. And this raises a stranger question that almost nobody talks about. What happens to a human fetus developing in Mars gravity or moon gravity? Bone density, vestibular development, cardiovascular development in the womb, all of it evolved under 1G. Nobody has ever answered this question, because it has never been tested on human subjects, and for extremely good ethical reasons, nobody is rushing to test it. While some animal studies on rodents in simulated partial gravity have shown developmental abnormalities, but translating that to human biology remains completely unknown. There's also the reverse problem, coming home. An astronaut who spends years in Martian gravity, then returns to Earth's full 1G, would face significant readaptation challenges, potentially worse than what astronauts experience today, simply because of the sheer duration involved. Would a Mars colonist who spent a decade at 38G even be capable of walking normally on Earth again? While some researchers have raised the possibility that long-term Mars residents could become permanently unsuited to Earth's gravity, a one-way biological ticket nobody currently has good data on. For the moon, the reverse trip problem is far less consequential simply because the trip itself is so much shorter and easier, but the underlying biology question is exactly the same, and it's a question neither destination currently has an answer to. There's a countermeasure angle worth mentioning too, because it's not as though researchers are simply throwing up their hands at this problem. Us astronauts today follow rigorous daily exercise regimens, roughly 2 hours per day, using specialized equipment like the Advanced Resistive Exercise Device, which uses vacuum cylinders to simulate weightlifting resistance in microgravity, specifically designed to counteract bone and muscle loss. These countermeasures have measurably reduced, though not eliminated, the severity of microgravity-induced conditioning compared to earlier space station eras before such equipment existed. It stands to reason that similar, likely less intensive, countermeasure regimens could meaningfully help lunar and Martian colonists as well, and this is an active area of ongoing research. But nobody yet knows exactly how much exercise is enough at 116G or 38G specifically, since all of the existing countermeasure research has been calibrated against 0G, not partial gravity, meaning even our best current mitigation strategies are, technically, an extrapolation rather than a proven solution for either destination. There's also a genuinely interesting proposed solution that shows up repeatedly in serious mission architecture discussions, but has never actually been built. Artificial gravity generated through rotation, either as a rotating section of a spacecraft during a long transit to Mars, or even, in more speculative long-term colony designs, as a rotating habitat structure on the surface itself. While physics here is well understood in principle, spinning a structure creates centrifugal force that mimics gravity, and it's been a staple of serious spaceflight engineering proposals since well before the space age even began, going back to design concepts published by figures like Wernher von Braun in the 1950s. The problem has never been the physics, it's the engineering scale required. Generating a comfortable, low nausea level of simulated gravity at a rotation rate the human inner ear can tolerate without inducing motion sickness requires a genuinely large rotating radius, large enough that no crewed spacecraft has ever actually built and flown one, and no habitat design has moved past the conceptual and small-scale prototype stage. If this technology matures in the coming decades, it could theoretically solve the gravity transit problem for the journey to Mars specifically, even if it doesn't solve the surface gravity question once colonists actually land. Since nobody is proposing rotating habitats large enough to contain an entire Martian or lunar colony city anytime soon. On gravity, Mars has the theoretical edge for long-term human biology, simply because 0.48 is a stronger gravitational signal than the Moon's 0.166, and most experts believe it will produce less severe physiological degradation. But less severe doesn't mean safe, and this remains one of the largest scientific gaps standing between us and either destination becoming a genuine, self-sustaining colony rather than a temporary outpost. Now let's talk about something that might be even more dangerous than gravity: radiation. Radiation problem Earth has something we almost never think about because it's invisible and it's always been there protecting us: a magnetosphere. A vast planet-wide magnetic field generated by the churning molten iron of our planet's outer core, which deflects the vast majority of dangerous charge, particles streaming toward us from the sun and from deep space. Neither the Moon nor Mars has anything like this protection anymore. The Moon has no global magnetic field and essentially no atmosphere at all. Its so-called atmosphere, technically called an exosphere, is so thin it contributes effectively nothing in terms of radiation shielding. This means the lunar surface is exposed to the full, unfiltered brunt of two dangerous radiation sources: galactic cosmic rays, extremely high-energy particles originating from outside our solar system, likely from supernova explosions, and solar particle events, bursts of radiation thrown off by the sun, particularly during solar flares and coronal mass ejections. Data from instruments on the Lunar Reconnaissance Orbiter and China's Chang'e 4 mission have measured radiation dose rates on the lunar surface, roughly 1,369 micrograys per day, translating to an annual dose several hundred times higher than what a person experiences on Earth's surface. Astronauts aboard the ISS, which still sits within Earth's protective magnetosphere, receive meaningfully less radiation exposure than they would standing unshielded on the lunar surface. Mars is genuinely a little better here, but a little better than catastrophic is still not good. Mars lost its global magnetic field billions of years ago, and scientists believe this loss is directly connected to why Mars also lost most of its atmosphere over geologic time, since without a magnetic field to deflect it, the solar wind is thought to have gradually stripped away the planet's air. What atmosphere remains today is extremely thin, only about 0.6% of Earth's atmospheric pressure at the surface. It's nowhere near enough to breathe or protect against temperature extremes, but it does provide some minor shielding against radiation, more than the Moon has, though far less than Earth's atmosphere provides. Measurements from NASA's Curiosity rover, using its radiation assessment detector instrument, found astronauts on the Martian surface would receive a radiation dose of roughly 0.64 millisieverts per day, extrapolating to somewhere around 233 millisieverts per year, still dramatically higher than Earth's natural background radiation, which averages around 3 to 6 millisieverts per year for most people, but noticeably lower than the unshielded lunar surface. Here's the part that should genuinely worry you if you're thinking about this as a real colonization proposal rather than a movie plot. The trip itself might be almost as dangerous as the destination. During the roughly 7-month transit to Mars, astronauts are exposed to the full radiation environment of deep space, with only the thin shielding of their spacecraft hood, while no planetary body blocking even half the sky. or Curiosity's own instruments, which measured radiation during its cruise to Mars back in 2011 and 2012, recorded that the round-trip trans alone could expose astronauts to a radiation dose close to or exceeding NASA's career exposure limits for increased cancer risk before they've even set foot on the planet. For long-term survival on either world, the solution scientists generally converge on is the same: get underground. Both lunar regolith and Martian regolith, piled several meters thick over a habitat, would provide substantial radiation shielding, comparable in some estimates to Earth's atmosphere. This is part of why so much of current colonization planning for both destinations revolves around lava tubes. Underground volcanic tunnels formed billions of years ago by flowing lava, confirmed by orbital radar and gravity data to exist on both worlds. A colony built inside a lava tube, or buried under several meters of packed regolith, could realistically shield inhabitants down to something close to background radiation levels. But that comes with an enormous engineering cost. It means giving up the idea of glass-domed cities with a view of the stars, and instead building colonies that function more like underground bunkers, at least for permanent, long-duration habitation. Surface time would need to be minimized and heavily suited, closer to deep-sea diving than backyard gardening. So on radiation, Mars technically has a lower surface dose than the Moon, thanks to its thin atmosphere providing at least some shielding, but the 7-month transit radiation exposure required just to get to Mars may functionally erase that advantage or worse. The Moon's radiation problem is more severe once you're there, but you're only exposed to the deep space radiation risk of the journey itself for 3 days, not 7 months. But it's worth spending a moment on shielding materials specifically, because pile regolith on top of the habitat is the standard answer, but it's not the only one being seriously studied, and the comparison between candidate materials is genuinely interesting. Water itself is an excellent radiation shield, which is part of why some habitat designs propose lining walls with water storage tanks, serving double duty as both life support resource and passive shielding. Hydrogen-rich materials in general tend to be particularly effective at blocking galactic cosmic rays, specifically because of how hydrogen nuclei interact with incoming high-energy particles, which is part of why some researchers have proposed polyethylene-based shielding materials, and why lunar and Martian ice deposits, being water-based and therefore hydrogen-rich, could theoretically serve a dual purpose as both a life support resource and a radiation shield if a habitat were built directly adjacent to or partially within an ice deposit. Regolith itself, while abundant and free in the sense that it doesn't need to be launched from Earth, is actually a somewhat less efficient shielding material per unit of mass than water or polyethylene, meaning a regolith-shielded habitat generally needs a thicker layer to achieve the same protection a thinner layer of water or hydrogen-rich material could provide. A genuinely important design trade-off between using an abundant local material inefficiently versus a scarcer, more efficient one. It's close, and it's ugly on both sides. Let's move to something a little more hopeful: water and resources. Water, AR, and raw materials. No colony survives on cleverness alone. It survives on water, on breathable air, on food, and on the raw materials needed to build and repair everything from habitats to spacesuits to spare parts. This is where the concept of ISRU comes in situ resource utilization, the space industry's term for using what's actually there instead of hauling everything from Earth. Let's start with water, because water is life, quite literally. What's needed for drinking, for growing food, for generating breathable oxygen through electrolysis, and even as a radiation shield and as a feedstock for rocket fuel. The Moon's water story is genuinely one of the more exciting scientific developments of the last 2 decades. For most of the 20th century, the Moon was assumed to be bone dry. That assumption started collapsing in the 2000s. NASA's ELSROS mission in 2009 deliberately crashed a rocket stage into a permanently shadowed crater near the lunar South Pole and detected a plume containing water ice. Since then, orbital instruments and NASA's SOFIA Airborne Observatory have confirmed water ice exists, trapped in permanently shadowed craters near both lunar poles, regions that never see direct sunlight and stay locked at extremely cold, stable temperatures, sometimes below -200 degrees Celsius. Cold enough to trap ice for potentially billions of years. This is precisely why NASA's Artemis program is targeting the lunar South Pole specifically, rather than the equatorial regions Apollo explored. Estimated quantities of ice vary significantly between studies, but some estimates suggest hundreds of millions to potentially billions of metric tons of water ice could be locked in these polar craters. That's a genuinely massive, potentially colony-sustaining resource if it can be efficiently extracted, which remains an unsolved engineering challenge. Since these craters are extremely cold, extremely dark, and extremely difficult to operate machinery in, Mars, meanwhile, has water in a completely different form and distribution. Rather than being concentrated in a few polar craters, Mars appears to have water ice spread more broadly, in polar ice caps visible from orbit, partly made of frozen water beneath a layer of frozen carbon dioxide, and also as subsurface ice detected at various latitudes, sometimes surprisingly close to the equator. NASA's Mars Reconnaissance Orbiter has identified ice deposits in mid-latitude regions that could be practically accessible with relatively shallow excavation. Missions like Phoenix directly confirmed water ice just beneath the Martian surface near the North Polar region back in 2008. In terms of raw accessibility, Mars may actually have an edge here. Its water resources appear less confined to a handful of extreme, permanently shadowed, difficult-to-reach polar craters and more distributed across regions that are easier to operate in with sunlight for solar power. Now let's talk about air, or more specifically, the raw materials needed to make breathable air and rocket fuel. Mars has a genuinely enormous advantage here, and it comes down to one molecule: carbon dioxide. Mars's thin atmosphere is roughly 95% CO2. It might sound useless at first, since CO2 isn't breathable, but it's actually an incredible resource, because through a well-understood chemical process called the Saba reaction, CO2 combined with hydrogen can be converted into methane and water, and the water can then be split via electrolysis into breathable oxygen and hydrogen, which can be fed right back into the process. NASA's MOXIE experiment, flown aboard the Perseverance rover, successfully demonstrated exactly this kind of in-situ oxygen production on the Martian surface, repeatedly generating breathable oxygen directly from the Martian atmosphere throughout its operational life, proving the underlying chemistry works in real Martian oceans. The same chemistry sits at the center of SpaceX's entire Mars architecture, because methane and oxygen are also rocket propellants, meaning a Mars colony would theoretically manufacture its own return fuel directly from the Martian atmosphere and ice deposits without needing to ship propellant all the way from Earth. A single fact is a genuinely massive strategic advantage for Mars, because it changes a return trip from impossible without a massive Earth-launched fuel supply to possible using local resources, at least in theory. The Moon has no atmosphere to work with in this way. There's no CO2 to harvest from the air because there effectively is no air. Lunar oxygen production instead relies on extracting oxygen chemically bound up in the regolith itself. Lunar soil is roughly 40 to 45% oxygen by weight, locked into minerals like ilmenite and various silicate compounds. Extracting it requires energy-intensive processes like molten regolith electrolysis or hydrogen reduction, technologies still largely experimental and not yet proven at any meaningful scale on the actual lunar surface, though multiple companies and space agencies are actively developing prototype systems for near-future missions. On raw materials for construction, both worlds offer regolith that can theoretically be used for 3D printing habitats, radiation shielding, and even solar cell production, through processes like sintering, where regolith is heated and fused into solid material without needing to haul concrete or metal from Earth. Both surfaces are also rich in useful metals, iron, aluminum, titanium, and more, locked in their respective soils and rocks, though extracting and refining them into usable form is a challenge neither world has solved at scale yet. There's one more resource worth mentioning, because it rarely comes up in casual comparisons but matters enormously for any long-term colony. Building a genuinely closed-loop life support system, one that doesn't need constant resupply of consumables from Earth, requires efficiently recycling water, air, and waste, not just extracting fresh resources from the environment. ISS today already recycles a substantial majority of its water, including, notably, water reclaimed from crew urine and cabin humidity, through a system called the Water Recovery System. And that recycling efficiency has steadily improved over the station's operational lifetime as the technology has matured. Any lunar or Martian colony would need an even more efficient version of this same closed-loop philosophy, because unlike the ISS, which can still receive periodic resupply shipments from Earth on a matter of months, A genuinely self-sufficient colony on either world needs its water and air recycling loops to be close to total, since the entire point of self-sufficiency is not needing that resupply lifeline at all. Neither the Moon nor Mars has any inherent advantage in this specific technology, since closed-loop recycling systems are largely destination-agnostic engineering, developed and refined primarily through ISS research. But it's worth flagging as a reminder that having local water and having a self-sufficient colony are two different achievements separated by a huge amount of additional life support engineering that applies equally to both worlds. Also, tallying it up, Mars wins decisively on atmospheric resources, thanks to that CO2-rich atmosphere enabling fuel and oxygen production through well-tested chemistry. Moon wins on concentrated, confirmed water ice deposits, though extraction remains a genuinely hard engineering problem in those brutal polar crab or conditions. It's a split decision, but Mars's atmospheric CO2 advantage, especially for fuel production and eventual return trips, might be the single most strategically important resource advantage either world holds. Next, let's talk about something that sounds almost trivial by comparison, but might actually be one of the hardest problems of all: the weather. Feeding a colony. None of the last 4 chapters matter if the colonists starve. And this might be the category where science fiction has done the most damage to public understanding, because in the movies, growing food on Mars or the Moon always looks like a so-loved problem. A few rows of potatoes under a dome, some grow lights, done. Reality is significantly messier, and it's worth walking through, because agriculture touches almost every other system we've already discussed: power, water, radiation, shielding, and even psychology. Let's start with the soil itself, because here's a fact that surprises almost everyone. You cannot simply plant seeds directly into lunar or Martian regolith to expect food to grow. Both soils are missing the organic matter, the nitrogen-fixing microbial ecosystems, and the balanced nutrient profile that Earth's soil has built up over billions of years of biological activity. Worse, Martian regolith in many regions contains perchlorates, a class of chlorine-based chemical compounds that are toxic to humans, and that would need to be washed out or chemically neutralized before the soil could safely be used to grow anything intended for human consumption. Perchlorate concentrations detected by the Phoenix lander and later missions have been high enough that direct food cultivation in raw, untreated Martian soil is considered a genuine health hazard, not just an inconvenience. Researchers, including teams at Wageningen University in the Netherlands, who have run some of the most detailed lunar and Martian regolith simulant growing experiments over the past decade, have had some real success growing crops like tomatoes, peas, rye, and cress in simulated regolith once it's been amended with nutrients, and, in several trials, organic matter derived from things like human waste or plant residue. These experiments are genuinely encouraging. Several crops in these simulant trials have produced yields not wildly different from Earth-based control soil, but they also confirm that raw regolith needs real processing before it becomes viable growing medium, and none of these experiments have yet been run in actual lunar or Martian gravity, only in simulated regolith chemistry under Earth gravity, which leaves the partial gravity effect on plant growth as another open question. This is why most serious near-term agricultural planning for both destinations leans less on farming the regolith and more on hydroponics and aeroponics, growing plants in nutrient-rich water solutions or nutrient mist, with no soil involved at all. This approach sidesteps the perchlorate and nutrient poverty problems entirely, dramatically reduces water usage compared to traditional soil farming since the water can be recirculated in a closed loop, and allows for vertical, stacked growing systems that make efficient use of limited pressurized habitat volume. NASA has already tested exactly this kind of system aboard the ISS through its veggie and advanced plant habitat experiments, successfully growing lettuce, radishes, and even chili peppers in microgravity using LED grow lights tuned to the specific light wavelengths plants need for photosynthesis. Light itself becomes a genuinely interesting point of comparison between the two destinations. On the Moon, outside the permanently shadowed polar craters, most locations experience roughly 2 weeks of continuous daylight followed by 2 weeks of continuous darkness. For agriculture, this actually simplifies some things and complicates others. During the lunar day, there's abundant, uninterrupted sunlight for solar power to run artificial grow lights or potentially even skylight-fed greenhouses, but during the 2-week lunar night, Any agriculture has to run entirely on stored power and fully artificial lighting since there's no sunlight at all. Mars, because it rotates roughly every 24 hours and 37 minutes, almost identical to an Earth day, actually offers a far more Earth-like day-night light cycle for plant growth, which matters more than people expect, because most crop species have circadian rhythms tuned to roughly 24-hour cycles, affecting everything from flowering time to nutrient uptake. Well, this is a genuinely underappreciated point in Mars's favor. Its day-length similarity to Earth isn't just a nice trivia fact. It's a meaningful agricultural and biological advantage that the Moon's 2-week day-night cycle simply cannot replicate without heavy artificial intervention. On the other hand, Mars's dust storms once again rear their head here, since any Martian agriculture relying even partially on natural sunlight through greenhouse structures would be vulnerable to the same kind of extended light blackouts that killed the Opportunity rover, reinforcing, yet again, why nuclear power rather than solar is increasingly treated as the safer baseline for permanent Martian infrastructure, agriculture included. And there's the question of caloric math, because growing a tomato is one thing, but feeding a colony of dozens or hundreds of people indefinitely without resupply from Earth is an entirely different scale of problem. Current NASA estimates for a self-sufficient closed-loop food system suggest that a genuinely Earth-independent colony would need a combination of high-calorie staple crops, things like potatoes, wheat, soybeans, and rice, grown at meaningful scale, alongside protein sources, which realistically means either lab-grown or cultured protein, insect farming, which is remarkably calorie and space-efficient compared to traditional livestock, or in a more distant future scenario, small-scale animal husbandry using animals like tilapia or chickens that require relatively modest space and resources per calorie produced. Neither the Moon nor Mars has any operational, food-producing agricultural infrastructure at this point in time. Everything described here remains at the research and small-scale prototype stage. When you weigh which destination has the structurally easier path to eventual food self-sufficiency, Mars again edges ahead, not because its soil is meaningfully better, both require significant processing, but because of that Earth-like day length, its comparatively milder day-to-day thermal environment inside a greenhouse structure, and its atmospheric CO2, which, beyond fuel production, is also a direct agricultural input, since plants consume CO2 during photosynthesis, and Mars has an abundant, free supply of it sitting right outside the greenhouse wall compared to the Moon, where CO2 for plant growth would itself need to be manufactured or recycled from human respiration in a tightly closed loop. On agriculture, a genuine, if narrow, edge to Mars, driven primarily by day-length similarity to Earth and atmospheric CO2 availability, offset by the same dust storm power vulnerability that haunts nearly every other Mars-related system in this video: temperature, weather, and the environment. Let's talk about what it's actually like outside, on the Moon. Because there's essentially no atmosphere to trap or distribute heat, the temperature swings are brutal and immediate during the lunar day, which lasts about 2 Earth weeks due to the Moon's slow rotation. Surface temperatures at the equator can reach roughly 127 degrees Celsius, about 260 degrees Fahrenheit, during the 2-week lunar night. That same spot can plunge to roughly negative 173 degrees Celsius, about negative 280 degrees Fahrenheit. That's a swing of nearly 300 degrees Celsius between lunar day and night, at the exact same location, with essentially no gradual transition, because without an atmosphere to diffuse sunlight or retain heat, the moment the sun sets, the ground begins radiating its heat directly into the vacuum of space with nothing to slow it down. Well, this is a genuinely enormous engineering problem, because it means any lunar habitat, rover, or piece of equipment has to survive a roughly 300 degrees Celsius thermal cycle every single lunar day-night period, about every 5 Earth days. Was part of why NASA is targeting the lunar South Pole for Artemis, not just for water ice, but because certain peaks near the pole experience what are called near-permanent sunlight, while nearby crater floors sit in near-permanent shadow, creating regions with far more thermally stable conditions than the wild equatorial swings, though even these regions still require serious thermal engineering. Mars, by contrast, has a genuinely more temperate, though still brutal, thermal environment, precisely because it does have a thin atmosphere that provides some heat distribution and insulation. Average surface temperature on Mars is around negative 63 degrees Celsius, about -81 degrees Fahrenheit, but because Mars is farther from the Sun and has a thin atmosphere. Temperatures still swing significantly by time of day and season, from highs that can reach around 20 degrees Celsius near the equator at midday during summer, down to lows of -143 degrees Celsius near the poles in winter. That's still an enormous range, but nothing close to the Moon's 300-degree day-night whiplash, because Mars's thin atmosphere, even at less than 1% of Earth's pressure, does enough to smooth out the most violent extremes. Then there's weather itself. And this is where Mars introduces a genuinely unique hazard that the Moon simply doesn't have, because the Moon has no atmosphere to generate weather of any kind. Mars has planet-wide dust storms, and they are not a minor inconvenience. Mars experiences regular regional dust storms, and roughly once every Martian year or so, which is about 2 Earth years, conditions can align to create a truly global dust storm that envelops the entire planet for weeks or even months at a time. The 2018 global dust storm was so severe, it's what ultimately killed NASA's solar-powered Opportunity rover, cutting off its access to sunlight for long enough that its batteries drained and it never woke back up, ending a mission that had already run for nearly 15 years, far beyond its original 90-year design life. For a Mars colony relying on solar power, this is an existential design constraint, not a footnote, because a storm that blocks out the majority of sunlight for weeks or months could cripple power generation right when a colony needs heating, oxygen production, and life support the most. This is a major reason why serious Mars colonization planning increasingly leans toward nuclear power, particularly small modular fission reactors, as a more storm-resistant baseline power source, rather than relying solely on solar arrays. NASA and the Department of Energy have already been developing exactly this kind of technology through projects like the Fission Surface Power Program, specifically with lunar and Martian surface power in mind. The Moon has no dust storms in the atmospheric sense, but it has its own version of the problem: lunar dust itself. Lunar regolith is famously nasty stuff, extremely fine, jagged at a microscopic level because there's no wind or water erosion to smooth its edge. Also, over billions of years, the way it happens on Earth, and electrostatically charged in a way that makes it cling to everything: spacesuits, equipment, seals, camera lenses, and lungs. Apollo astronauts reported that lunar dust caused irritation, damaged suit seals, and even had an odor some described as similar to spent gunpowder once it was tracked back inside the lunar module. Long-term exposure risks from lunar dust, sometimes discussed under the informal term lunar hay fever, remain a genuine, unresolved health and equipment durability concern for any long-duration lunar mission. Mars dust has similar abrasive properties, though decades of weak wind erosion on Mars have smoothed it slightly more than lunar dust, which has never experienced any erosion at all in its multi-billion-year history. On environment, Mars wins on raw thermal stability, since its atmosphere, thin as it is, prevents the catastrophic 300-degree day-night swings the Moon experiences. But Mars introduces the unique, colony-threatening hazard of global dust storms that can choke off solar power for months, a problem the Moon simply does not have. The Moon's environmental hazard is instead the punishing, unrelenting thermal cycle and its nasty, equipment-damaging dust. Either one is remotely close to comfortable. Both require genuinely serious, still partially unsolved engineering to survive long-term. Let's talk about the thing that turns surviving into actually living. How you build a home there in the first place. Well, a habitat. You cannot just live in a tent on the Moon or Mars. You need pressurized structures, radiation shielding, airlocks, and life support systems that can run reliably for years without a hardware store anywhere nearby. Well, so how do the two compare when it comes to actually constructing a colony? Let's start with the raw material both worlds have in abundance: regolith, the loose, fragmented rock and dust that covers the surface of both bodies. Both lunar regolith and Martian regolith have been studied as potential 3D printing feedstock, the idea being that autonomous printers could arrive ahead of any human crew and begin constructing habitat shells, landing pads, and radiation shielding berms using local material, dramatically reducing the mass that has to be launched from Earth. NASA's 3D Printed Habitat Challenge and various university and private research programs have already tested regolith simulants, synthetic material, designed to closely match the real thing, in 3D printers, successfully producing solid, structurally sound test walls and components. For radiation shielding specifically, both worlds benefit enormously from the same basic strategy: piling meters of regolith over or around a habitat, or better yet, building inside a natural cavity that already provides that shielding for free. And this is where lava tubes become genuinely one of the most exciting prospects for both destinations. Lava tubes are naturally occurring tunnels formed when the outer layer of a flowing lava stream cools and solidifies while lava continues flowing underneath, eventually draining out and leaving a hollow tube behind. On Earth, we have plenty of these, some large enough to walk through comfortably. On the Moon and Mars, because gravity is so much lower, these tubes can be dramatically larger. Orbital imaging has identified potential lunar lava tube openings called skylights in regions like the Marius Hills, with some models suggesting these tubes could be wide enough and tall enough to contain entire small cities, potentially hundreds of meters across. Well, candidate lava tube openings have been identified on Mars as well, particularly around the Tharsis volcanic region. A colony built inside a lava tube would get radiation shielding, thermal stability, and protection from micrometeorite impacts essentially for free, all provided by tens of meters of solid rock overhead, dramatically reducing the amount of artificial shielding engineers would otherwise need to build and haul. The catch is that we still don't have confirmed, ground truth data on the structural stability of these formations, their exact internal dimensions, or whether they're even navigable and safe to build inside. That verification will likely require actual robotic or human reconnaissance missions in the coming years on both worlds. Now, where does Mars pull ahead? Atmosphere-related construction advantages. Because Mars has some atmospheric pressure, even at less than 1% of Earth's, habitat structures on Mars face a smaller pressure differential between inside and outside, compared to the Moon, which is a true hard vacuum. This isn't a massive difference in engineering terms, but it does mean slightly less catastrophic structural stress in the event of a breach, and marginally simpler pressure vessel design. Where does the Moon pull ahead in construction? Or power reliability outside of the harsh 2-week night cycle, and proximity for resupply, which we already covered, meaning any construction mistake, missing part, or design flaw discovered mid-build could realistically be corrected with a follow-up shipment from Earth within days to weeks, rather than the 26-month wait a Mars mission might face if it misses a launch window. There's also a subtler factor that colonization planners increasingly emphasize. The Moon functions as an ideal proving ground. Nearly every core technology a Mars colony will eventually need, closed-loop life support, ISRU oxygen and water extraction, radiation-shielded habitat construction, ion long-duration dust mitigation, autonomous construction robotics, can be developed, tested, and refined on the Moon first, where mistakes are recoverable within days before ever being deployed on Mars, where mistakes might not be recoverable for years. The Moon as testbed for Mars philosophy is explicitly part of NASA's stated long-term strategy, often summarized with the phrase, "on to Mars." One more construction factor worth mentioning is workforce, specifically, who or what actually does the building, well, given the extreme radiation exposure and thermal hazards of surface work on either world. Current planning for both destinations leans heavily toward robotic and autonomous construction preceding any human arrival, with astronauts moving into structures that robots have already substantially built, rather than astronauts themselves doing extensive manual surface construction in bulky pressurized suits. NASA and several private companies have already tested early autonomous regolith moving and 3D printing robotic systems in Earth-based analog environments designed to mimic lunar and Martian regolith conditions, though none of this technology has yet been proven operating for extended periods in the real thermal, vacuum, or low-gravity conditions of either actual destination. Moon's proximity again offers a meaningful advantage here, since any autonomous construction robot malfunctioning or getting stuck on the lunar surface could realistically be diagnosed and potentially even physically serviced by a follow-up mission on a timescale of weeks, while the same failure occurring on Mars might sit broken, unrepaired for the better part of 2 years until the next favorable launch window allows a replacement part or repair mission to actually arrive. On habitat construction specifically, it's close to a draw on raw technique, since both worlds share the same fundamental regolith-based, lava tube-focused strategy. But the Moon holds a meaningful practical advantage as the safer place to actually develop and debug these technologies first, precisely because of that proximity advantage from Chapter 1. Now let's get into something that almost never comes up in space documentaries, but that lawyers, diplomats, and policy researchers argue about constantly. Who actually owns any of this? And who's in charge once people are living there? Well, UO's in charge, and who owns it? Here's a question that sounds almost silly until you actually sit with it. If a private company builds a mining operation on the moon and extracts water ice from a crater, who does that water actually belong to? The legal foundation for everything happening in space today traces back to the Outer Space Treaty of 1967, a Cold War-era agreement ratified by the United States, the Soviet Union, and dozens of other nations that explicitly states no nation can claim sovereignty over the moon, Mars, or any other celestial body. It's often summarized as banning any country from planting a flag and declaring ownership the way European colonial powers once did on Earth. It sounds admirably egalitarian, and in many ways it is, but it was written in an era when nobody seriously expected private companies to be doing any of this, and it leaves us enormous, still unresolved ambiguity around resource extraction specifically. Banning national sovereignty also ban a private company from extracting and selling lunar water ice or Martian minerals. The treaty doesn't clearly say, and different nations have started interpreting it differently. The United States passed its own domestic legislation, the Commercial Space Launch Competitiveness Act of 2015, asserting that American license and companies have the right to own and sell resources they extract from celestial bodies, even though they can't claim the land itself. Luxembourg passed similar legislation shortly after, explicitly positioning itself as a friendly jurisdiction for space mining companies. More recently, NASA has spearheaded the Artemis Accords, a series of bilateral agreements now signed by dozens of countries that lay out shared principles for lunar exploration, including provisions for what the Accords call safety zones around lunar operations, essentially buffer areas where other nations' astronauts and spacecraft are expected to coordinate before entering to avoid interference or accidental collision with active operations. Notably, China and Russia are not signatories to the Artemis Accords and are instead pursuing their own separate lunar framework through the International Lunar Research Station Initiative, meaning the moon may end up, at least for a while, with two parallel, not entirely compatible sets of operating rules governing different coalitions of countries working in the same physical region, particularly around that same scientifically valuable South Pole. This matters enormously for the moon specifically, more than it currently matters for Mars, precisely because the moon's most valuable known resources, those permanently shadowed polar water ice deposits, are concentrated in a genuinely limited number of physical locations. Unlike Mars, where water ice appears to be spread across a much broader range of latitudes and terrain, the moon's best water ice sites are a comparatively small handful of specific craters near the South Pole. Geographic concentration raises real, near-term questions about competition and potentially conflict between multiple nations and companies all racing to claim practical access to the same physically limited handful of prime crater locations, even without any formal claim of sovereign ownership. Mars, being both farther away and less immediately economically attractive in the near term, has generated less urgent legal wrangling so far, simply because nobody is racing to extract and monetize Martian resources on any comparable near-term timeline, the way multiple nations and companies are actively racing towards specific lunar polar sites right now. But Mars raises its own distinct and genuinely fascinating governance question, one that's less about resource competition and more about the nature of authority itself. What happens to national or corporate authority over a colony that exists 9 to 24 minutes of communication delay away from any government capable of actually enforcing law over in real time? Elon Musk has publicly floated the idea that a self-sufficient Mars colony might eventually govern itself independently, subject to what he has described as a set of foundational principles rather than continued oversight by any single Earth government or company, and SpaceX has previously included language in its Starlink user agreements gesture, pointing toward a self-governance model for Mars, treating Mars as a jurisdiction that shouldn't automatically inherit the full body of Earth-based national law by default. This is, to put it mildly, a legally and politically fraught proposition, and most international law scholars remain skeptical it would hold up as a genuinely independent legal framework in any way Earth-based governments would readily recognize or defer to, particularly if American citizens are involved, since the Outer Space Treaty explicitly holds launching nations internationally responsible for the activities of their own non-governmental entities in space, including private companies, no matter how far away or how independent those entities eventually claim to become. It was also a much more mundane, but equally unresolved, governance question sitting underneath all of this. What body of law actually applies day to day to something as basic as a workplace dispute, a medical emergency requiring a difficult ethical decision, or In an extreme case, an actual crime, committed in a habitat that is legally part of any nation's sovereign territory. NASA and international partners have already had to think through early versions of this question aboard the International Space Station, where a detailed intergovernmental agreement specified whose national law applies to which module and which nationality of crew member in different scenarios. Scaling that same kind of legal patchwork to a permanent, growing multinational colony of hundreds or eventually thousands of people on either the Moon or Mars remains a genuinely open institutional design problem that no space agency, company, or international body has fully solved yet. On governance specifically, this isn't really a which world wins category the way the others have been. It's more of a shared unresolved problem, but it does weigh differently on each destination. Moon's governance tension is nearer term and more urgent, driven by geographic competition over a small number of prime polar resource sites among multiple by competing nations and companies right now, in this decade. Mars's governance tension is more theoretical for now, but ultimately more radical in what it questions, namely whether any Earth-based legal authority can meaningfully govern a population that lives, generation after generation, up to 40 minutes of communication delay away. There's one more governance wrinkle worth flagging, because it touches directly on the economics chapter coming up next. The question of taxation and citizenship. If a colonist is born on the Moon or on Mars, to parents of different nationalities, working for a multinational consortium of companies and space agencies, what nationality does that child hold? What country, if any, has taxing authority over their eventual earnings? And which country's court system, if any, would handle a legal dispute they were involved in as an adult? These aren't science fiction hypotheticals dreamed up for dramatic effect. They're the exact kind of jurisdictional question that international law scholars and space policy researchers are already actively publishing papers about today, well before a single child has actually been born off-world, precisely because getting ahead of these questions before they become urgent, lived realities is far safer than trying to improvise answers after the fact, with real families and real disputes already in the balance. Let's zoom out from law and policy entirely and look at exactly who is racing toward each of these destinations right now, with real hardware and real deadlines. While communication and PSN and psychological isolation numbers and radiation charts are one thing. But colonies aren't built by robots alone, they're built and lived in by human beings, and human beings are not built for isolation. Well, this is a category that doesn't get nearly enough attention in most space content, and it might end up being one of the most decisive practical differences between these two destinations. Let's talk communication delay first, because we touched on this back in Chapter 1, but it deserves its own deeper look here. On the Moon, radio signals traveling at the speed of light take roughly 3 seconds to reach Earth one way, meaning a round-trip conversation has a delay of about 6 seconds. That's noticeable, but it's manageable, roughly comparable to a laggy international phone call. Astronauts on the lunar surface can have something close to real-time conversations with mission control, can get near-immediate answers to urgent questions, and crucially, can have real-time video calls with family back on Earth. From Mars, the delay is a completely different animal, depending on the relative positions of Earth and Mars in their orbits. One-way communication delay ranges from about 4 minutes at closest approach to over 24 minutes at the farthest point, when the two planets are on opposite sides of the Sun, a period during which direct communication becomes essentially impossible for a stretch of time called solar conjunction, when the Sun itself physically blocks the radio path between the two planets for roughly 2 weeks every synodic period. Think about what this actually means day-to-day for a Mars colonist. No real-time conversations with anyone on Earth, ever. Every message is more like an email than a phone call. You send it, then wait anywhere from 8 minutes to nearly 50 minutes for a reply, assuming the other person responds instantly, which they won't. Want to ask mission control a question during an emergency? You'd better already know most of the answer yourself, because by the time help arrives, the situation may have already resolved itself, one way or another. This has genuine, serious psychological implications, and it's not speculation. It's informed by decades of isolation research from Antarctic research stations, submarine deployments, and long-duration spaceflight analog studies like NASA's HIC's program in Hawaii, which simulated Mars mission conditions, including communication delay for periods of up to a year at a time. Findings from these analog studies and from actual long-duration ISS missions consistently point to real risks: depression, anxiety, interpersonal conflict within small, isolated crews, sleep disruption, and a phenomenon researchers sometimes call the third quarter effect, a dip in morale that tends to occur after the initial excitement fades and before the return home becomes imminent, right in the psychologically grueling middle of a long mission. For a Mars colonist, there may be no return home becomes imminent for years, which is an entirely different psychological weight than anything humans have collectively experienced before, even compared to the most extreme Antarctic winter-over researchers, who at minimum still have same-day email access to family. The moon's proximity offers a genuine, meaningful psychological safety valve that Mars simply cannot replicate. Near real-time contact with Earth, the psychological reassurance that home is only 3 days away if things go seriously wrong. And, importantly, the ability to actually see Earth in the sky, a bright, blue, obviously living world hanging there as a constant, visible reminder of home. From the Martian surface, Earth is nothing more than a faint blue-white dot, often not even visible depending on the time of day, indistinguishable to the naked eye from any other star. There's also crew composition and colony scale to consider. Early moon missions can rotate crews relatively frequently, given the short and low-risk transit, meaning individual astronauts don't need to endure years of isolation before rotating home. Early Mars missions, by contrast, are essentially locked into multi-year commitments once the crew departs. Because of that 26-month launch window cycle, you stay roughly 18 months to make the most of your time before the next efficient return window opens, and then you undertake another 7-month transit home. A round-trip crewed Mars mission, launched to return, is realistically a 2 to 3 year commitment, with no meaningful way to shorten it once you've departed. It's worth digging a bit deeper into what these analog missions have actually found, because the findings are more specific and more useful than a general "isolation is hard" conclusion. NASA's ACES program, which ran multiple missions inside a dome habitat on the isolated slopes of Hawaii's Mauna Loa volcano between 2013 and 2018, deliberately incorporated a simulated Mars realistic communication delay into its crew's daily life, and researchers tracking crew psychology across these missions documented measurable declines in crew cohesion and increases in interpersonal friction as missions progressed, particularly during the middle portion of longer, roughly 8 to 12-month missions, closely matching the third quarter effect pattern that had previously been documented in Antarctic winter-over research. Currently, Russia's Mars 500 experiment, conducted between 2010 and 2011, isolated a 6-person international crew inside a sealed facility for 520 days, deliberately matching the full duration of a realistic round-trip Mars mission including surface time, and documented similar findings, including one crew member developing a depressive episode significant enough to be specifically flagged in the mission's published psychological research findings, along with measurable interruptions to crew members' sleep-wake cycles that persisted for much of the isolation period. These findings matter because they're not simply describing isolation in the abstract, they're specifically describing what happens to small, high-stakes crews under communication delay conditions that closely mirror actual Mars mission timelines, which makes them among the most directly relevant psychological data points we currently have for this entire debate. Crucially, none of these analog missions have ever attempted to simulate the moon's much shorter, much lower delay conditions specifically, because researchers generally don't consider lunar duration isolation timescales to represent a comparable psychological research priority, which is itself a quietly telling signal about how much less severe the psychological challenge is generally understood to be for lunar duration missions compared to Mars duration ones. Well, in this category, there's no real contest. The moon offers vastly superior psychological conditions for colonists, meaningful real-time contact with Earth, visible reassurance in the sky, and realistic rescue and rotation timelines. Mars offers profound isolation, delayed communication that makes real conversation impossible, and multi-year commitments with no early exit option. This is a moon win, and it's not close. Now let's zoom out from human biology and psychology and talk about money, because at the end of the day, none of this happens without someone willing to pay for it. Another money question colonization is, whether we like it or not, fundamentally an economic problem before it's anything else. Rockets cost money. Life support costs money. Every kilogram launched into space costs money, and that cost scales dramatically with distance, mission duration, and the amount of redundancy required to keep people alive. Let's start with launch cost per kilogram, because this number underpins everything else. Historically, Launching mass to low Earth orbit costs somewhere in the range of $10,000 to $20,000 per kilogram using traditional expendable rockets. Rise of reusable rocket technology, particularly SpaceX's Falcon 9 and Falcon Heavy, has driven that number down dramatically, with current estimates for Falcon 9 launches to low Earth orbit frequently cited in the range of roughly $1,500 to $2,700 per kilogram. SpaceX's fully reusable Starship system is explicitly designed with the goal of pushing that number down even further, though it hasn't yet been proven at full operational scale, and cost figures remain projections rather than confirmed operational numbers. Low Earth orbit is just the starting line. Getting mass beyond LEO, to the Moon or to Mars, requires additional propulsion stages and additional fuel, multiplying the effective cost per kilogram delivered to the actual surface. For the Moon, because the trip is short and the delta V, the total velocity change required to get there and land is comparatively modest. Cost per kilogram delivered. A lunar surface, while still expensive, is more tractable using current and near-term technology. NASA's Commercial Lunar Payload Services program, which contracts private companies to deliver payloads to the lunar surface, has already deployed multiple missions and represents a live, functioning commercial market, generally operating in a more approachable cost range than equivalent Mars delivery would require. For Mars, the numbers get significantly more painful. A trip requires far more fuel due to the greater delta V needed, far more life support consumables to sustain any crew across a 7-month transit each way, and dramatically more redundancy given the impossibility of quick resupply or rescue. Elon Musk and SpaceX have publicly stated ambitions to eventually drive the cost of Mars transport down dramatically through full Starship reusability and in-situ propellant production on the Martian surface. But these figures remain aspirational projections rather than demonstrated costs, and most independent aerospace economists remain considerably more conservative in their estimates until reusable Starship Mars missions actually fly and their real costs become known. There's also the question of what each destination can plausibly generate in near-term economic return, because a colony that costs money forever with no path to any revenue is a much harder sell to governments and investors than one with even a distant path to self-sufficiency or export value. The Moon has a couple of genuinely credible near-term economic angles. First, it could serve as a fuel depot and staging point for deeper space missions, including Mars missions themselves, since lunar-derived propellant launched from the Moon's much shallower gravity well could theoretically be far cheaper to use for refueling spacecraft headed elsewhere than propellant launched all the way up from Earth. There's been serious, if not yet proven at scale, discussion of helium-3 as a potential lunar export, an isotope rare on Earth but present in the lunar regolith from billions of years of solar wind deposition, theoretically valuable as fuel for future fusion reactor designs, though this remains speculative until commercially viable fusion technology itself exists. And perhaps most immediately practical, lunar tourism and lunar science infrastructure represent a nearer-term, lower-risk revenue stream, given the relatively short and safe transit. Mars has a much harder time articulating any near-term economic return. It's simply too far and too expensive to ship anything back to Earth for profit in any near-term scenario. Its economic case, as currently articulated by proponents like SpaceX, rests less on near-term profit and more on a longer-term civilizational argument. The idea of Mars as a genuine backup for humanity, a hedge against existential risks to Earth, which is a compelling philosophical case, but a much harder one to fund for traditional investment or near-term government budget cycles that typically look ahead in increments of just a few years. Government space agency budgets and stated priorities also reflect this economic reality quite clearly. NASA's Artemis program, currently the agency's dominant crewed exploration priority, is explicitly moon-focused in its immediate, funded phases, with Mars framed as a longer-term follow-on goal built using lessons and technology developed through the lunar program first. China's space program has similarly prioritized lunar activity in its near-term crewed and robotic mission roadmap, including its own International Lunar Research Station initiative, planned in partnership with Russia and other nations, targeting the lunar South Pole region on a similar timeframe to NASA's Artemis efforts. It's worth putting some rough, illustrative shape around just how large these budget gaps actually are. NASA's Artemis program, across its full multi-mission scope including the Space Launch System rocket, the Orion spacecraft, ground systems, and the Human Landing System contracts, has been publicly estimated by NASA's own Office of Inspector General to cost on the order of tens of billions of dollars across the program's first several missions alone, a figure that has drawn its own share of congressional scrutiny and criticism for cost overruns and schedule delays, which is worth acknowledging honestly rather than presenting Artemis as some perfectly efficient counterexample to Mars' ambitions. But crucially, that spending is already appropriated, already flowing into contracts, and already producing flown hardware. Artemis I already happened. The Orion capsule has already flown around the moon and safely returned. Mars equivalent crewed program, by contrast, has no comparable currently appropriated multi-year government budget commitment anywhere in the world, meaning any account only of the cost of a crewed Mars program today is necessarily a projection built on assumptions, not a real, currently executing line item in any national budget the way Artemis already is. Well, this is also reflected in how private investment has flowed into the two destinations. Lunar-focused private companies, particularly those participating in NASA's Commercial Lunar Payload Services program, have secured real, signed, multi-mission contracts worth hundreds of millions of dollars collectively, money that is already being spent building and flying actual hardware on a multi-year cadence. Mars-focused private investment, by contrast, is overwhelmingly concentrated in a single company, SpaceX, and is functionally inseparable from that company's broader Starship development program, which itself serves multiple customers and purposes: commercial satellite launch, NASA's lunar lander contract, Mars ambitions, all bundled into one vehicle program, making it genuinely difficult to isolate how much investment is specifically Mars-directed versus simply general Starship development that happens to also serve Mars ambitions as a longer-term goal. On pure economics and near-term funding reality, the moon has a substantially stronger case. It's cheaper to reach, cheaper to resupply, has more plausible near-term revenue angles, and is where essentially every major national space agency has actually allocated their current, funded, non-speculative budget dollars. Mars's economic case remains largely aspirational, resting on long-term reusability projections and civilizational arguments rather than demonstrated near-term costs or revenue. Now, before we get to the final verdict, let's take a step back and look at exactly who is actually racing toward each of these destinations right now with real budgets, real hardware, and real deadlines, because the honest, on-the-ground answer to which one is humanity actually prioritizing is more interesting and more revealing than any single technical category we've covered so far. The global race. Let's talk about what's actually being built right now by whom, because theory is one thing, but hardware on a launch pad is a much more honest signal of genuine priority than any mission statement or press conference. NASA's Artemis program is, without question, the most heavily funded and most advanced near-term crewed lunar effort currently underway. Artemis I, an uncrewed test flight of the Orion spacecraft and the Space Launch System rocket, successfully flew around the moon and back in late 2022, validating the core hardware. Subsequent Artemis missions are planned to build toward a crewed lunar flyby, and eventually a crewed landing near the lunar South Pole using SpaceX Starship Human Landing System variant as the vehicle that will actually carry astronauts down to the surface, a genuinely interesting detail, since it means NASA's flagship lunar program depends heavily on hardware originally developed with Mars in mind, reinforcing that Moon to Mars isn't just a slogan, it's baked directly into the hardware dependencies of the program itself. Alongside the crewed missions, NASA's Commercial Lunar Payload Services program has already sent multiple robotic landers to the lunar surface through partnerships with private companies like Intuitive Machines and Firefly Aerospace, testing landing technology, prospecting instruments, and communication relay systems, ahead of any crewed return. While China's lunar ambitions are advancing on a genuinely comparable timeline, and arguably with less public schedule slippage than NASA has experienced. While China National Space Administration has already successfully executed multiple robotic sample return missions, including Chang'e 5, which brought lunar samples back to Earth in 2020, and Chang'e 6, which achieved the first ever sample return from the far side of the moon in 2024. China has publicly stated ambitions for a crewed lunar landing before the end of this decade and is developing the necessary new generation crewed spacecraft and lunar lander hardware in parallel, while simultaneously building out the International Lunar Research Station concept in partnership with Russia and a growing list of other participating nations, explicitly targeting the lunar South Pole, the same broad region NASA's Artemis program is targeting, which is precisely why the safety zone and coordination provisions discussed in the previous chapter matter so much right now. not as some abstract future concern. India, through its Chandrayaan program, became in 2023 the fourth nation to successfully soft-land a spacecraft on the moon, and the first to do so near the lunar South Pole specifically. With its Chandrayaan-3 mission's Vikram lander, India has since announced ambitions for its own crewed lunar mission later this decade, building on the human spaceflight capability it's developing through its Gaganyaan crewed orbital program. Japan, through its space agency JAXA, achieved a precision landing with its SLIM spacecraft in 2024, demonstrating pinpoint landing accuracy, a matter enormously for targeting the small, specific crater regions where the best water ice deposits are believed to be concentrated. Mars, by comparison, has seen extensive robotic exploration, but far less near-term crewed mission planning with hard, funded dates attached. NASA's Perseverance rover and Ingenuity helicopter have been operating on the Martian surface since 2021, and the agency's long-term Mars sample return program, though it has faced serious cost overruns, schedule delays, and a significant 2024 restructuring after an independent review found its original plan unrealistic, is aimed at bringing a small collection of Martian rock samples back to Earth for detailed laboratory analysis sometime in the following. China's Tianwen-1 mission successfully placed an orbiter and the Zhurong rover on Mars in 2021, and China has announced its own ambitions for a Mars sample return mission on a roughly similar timeline to NASA's effort, alongside publicly stated long-term aspirations for crewed Mars missions sometime around the 2030s or 2040s, though with considerably less specificity than its lunar roadmap. While SpaceX remains the clear outlier and the most aggressive voice specifically pushing Mars as a near-term crewed destination, with Elon Musk repeatedly stating ambitions for uncrewed Starship cargo missions to Mars within the current decade, followed by crewed missions to follow depending on how those uncrewed tests go. Well, it's worth being clear-eyed here. These specific timelines have slipped significantly and repeatedly over the years since they were first announced, and most independent aerospace analysts treat SpaceX's public Mars dates as aspirational upper bounds on ambition rather than reliable schedule commitments, particularly given that Starship itself, while making major, genuinely impressive progress through its test flight campaign, is still working through orbital refueling, long-duration deep space life support, and a functioning crewed variant, all of which are prerequisites for any actual Mars mission, and none of which have been fully demonstrated yet. Put all of this together, and a clear pattern emerges. Every major government space agency on Earth, without exception, currently has funded, scheduled, hardware-in-progress missions targeting the Moon, with crewed lunar landings realistically expected across multiple nations within roughly the next 5 to 10 years. Mars, by contrast, has abundant robotic exploration and enormous public enthusiasm, but not a single government space agency currently has a funded, scheduled, hardware-in-progress crewed Mars mission with a specific target date inside that same near-term window. Only organization pushing an aggressive near-term crewed Mars timeline is a private company, and even that company's own timelines have consistently proven more optimistic than what has actually happened. This is, in its own way, the single clearest piece of evidence for the Moon then Mars argument this video has been building toward. It's not a philosophical preference. It's simply where the actual funded hardware, the actual launch schedules, and the actual astronaut training programs are pointed across every major spacefaring nation on Earth right now in this decade. Before we get to the final verdict, let's address the objections. Because if you've spent any time in the comment sections of space channels on this platform, you already know exactly what's coming. And it's worth actually engaging with these arguments, honestly, rather than pretending they don't exist. He'd addressing the objections. The Moon is a dead end. It can never be truly self-sufficient. So why waste time and money there at all when Mars is the real prize? This is probably the single most common objection to the Moon first argument, and it deserves a serious answer rather than a dismissal. Honest response is that this objection is correct about the Moon's ultimate ceiling and wrong about what that ceiling actually implies. What will be serious in this debate is arguing the Moon should be humanity's permanent, primary home. Argument is that the Moon is the place where we develop and de-risk the technologies Mars will need, at a fraction of the cost and risk of doing that same development work on Mars itself. Skipping the Moon doesn't get you to a self-sufficient Mars faster, it gets you to Mars with unproven life support, unproven partial gravity biology, and unproven ISRU technology, tested for the first time in the one place on this list where testing failures are least survivable. moon isn't the destination in this argument. It's the workshop. Elon Musk has already said SpaceX is going straight to Mars. They're barely bothering with the moon at all. So clearly the private sector thinks Mars first is the right call. Well, this one is worth correcting directly because it's simply not accurate to the current state of the actual program. SpaceX is, right now, under contract with NASA, actively developing a lunar-specific variant of Starship as the human landing system for the Artemis program. The vehicle explicitly intended to carry the first Artemis astronauts down to the lunar surface. Whatever Elon Musk's personal, long-stated founding ambitions for Mars may be, SpaceX as a company is simultaneously one of the most heavily invested private entities in near-term lunar hardware development on the planet right now. Public rhetoric and the actual funded engineering roadmap are not the same thing, and this video has tried, throughout, to follow the second one rather than the first. Radiation and gravity concerns are overblown. Humans are adaptable. We'll figure it out once we're actually there, just like every other frontier in history. This is an appeal to historical optimism, and while human adaptability has indeed been remarkable throughout history, it's worth being precise about what makes this frontier different from previous ones. Every previous human frontier, however extreme, from polar expeditions to high-altitude settlement to deep ocean voyages, still took place under Earth's gravity and within Earth's magnetosphere. There is no historical precedent anywhere for multi-generational human biology operating outside both of those conditions simultaneously for years or decades at a stretch. We'll figure it out is a reasonable attitude towards solvable engineering problems, and most of the problems in this video are solvable engineering problems. It is a considerably riskier attitude toward open questions in fundamental human reproductive and developmental biology, where the honest answer is that we don't yet know if there even is a solution within the biological constraints we're working with. And the only way to find out involves actual human beings, potentially including children born in these environments, serving as the test subjects. This whole video ignores the fact that governments move too slowly. Real progress in space now happens through private companies moving fast, so the traditional moon roadmap doesn't really matter anymore. There's real truth buried in the premise here. Private companies genuinely have accelerated the pace of hardware development and driven down launch costs dramatically over the past decade, and that shift is one of the most important stories in this entire field. But the conclusion doesn't follow from the premise, because even the most aggressive private companies operating in this space, SpaceX chief among them, are still bound by the same underlying physics, the same radiation environment, the same communication delays, and the same partial gravity biology questions this entire video has walked through. Moving fast doesn't change the distance to Mars, or the duration of the transit, or how the human body responds to 38G over a decade. Private companies can compress timelines and cut costs, and they've already proven that dramatically, but they can't compress physics. And the sequencing argument in this video is built on physics and biology, not on bureaucratic pace. Well, isn't this whole video just restating the boring establishment consensus that NASA already believes? Where's the actual insight? Fair challenge and worth answering honestly rather than defensively. Yes, Moon then Mars is indeed NASA's own stated official position, and it would be dishonest to pretend this video arrived at some radical, contrarian conclusion nobody else has considered. But the value of this video was never meant to be, here's a secret answer nobody else has. It was meant to be, here's exactly why that consensus position actually holds up, category by category, once you do the work of walking through the real numbers instead of just accepting or rejecting the conclusion based on vibes. A huge amount of space content on this platform either blindly repeats, Mars is our destiny, without engaging with a single one of the categories in this video, or blindly dismisses Mars ambitions as pure fantasy without engaging with the genuine, serious progress being made on the underlying technology. The goal here was to actually show the work. Why does any of this actually matter to me, sitting here watching a YouTube video, rather than working at NASA or SpaceX? Wasn't this just abstract engineering trivia? This is worth answering sincerely, because it's a completely reasonable thing to wonder. Honest answer is that this decision, more than almost any other current scientific and engineering question, is going to shape the next century of human civilization in ways that will eventually touch everyone, not just engineers and astronauts. If humanity successfully establishes a genuinely self-sufficient off-world colony within the coming decades, It represents the first time in the roughly 300,000-year history of our species that human life has existed in a meaningfully permanent way beyond a single planet, a milestone with implications for long-term species survival that go well beyond any single mission or budget line. And even short of that grand outcome, the specific technologies being developed and tested for this exact debate, closed-loop life support, radiation shielding materials, autonomous construction robotics, in-situ resource extraction have plausible, meaningful applications back here on Earth too, in disaster response, in remote and extreme environment habitation, and in resource extraction technology for increasingly resource-constrained regions of our own planet. Understanding this debate properly isn't just trivia, it's understanding one of the genuine hinge points of where our species goes next and why. Now, with the objections addressed honestly, let's bring all of this together and ask the question this entire video has been building toward one final time. Does either of these destinations actually win outright? Or is the real answer something neither side of this debate usually wants to admit? The verdict nobody wants to hear. Let's tally the categories one more time, plainly pull on every thread from this entire video into a single honest scoreboard. Distance and accessibility. Moon, decisively. 3 days versus 7 months isn't a close call, and the difference in emergency survivability alone, days to rescue versus years to resupply, arguably outweighs several of the other categories combined. Gravity and long-term human biology. Mars has the theoretical edge, since 0.48 G is likely a stronger, healthier signal for the human body than the Moon's 0.166 G, though this remains genuinely unproven for either destination, and stays one of the largest open questions in this entire debate. Radiation. A near draw, arguably a slight edge to Mars on surface dose thanks to its thin atmosphere, but that advantage is likely erased or worse by the far longer, far more radiation-exposed transit required just to get there, meaning the true total dose comparison may actually favor the Moon once transit exposure is honestly included. Water and resources. Split. The Moon has more concentrated, confirmed polar ice. Mars has more broadly distributed ice deposits and, critically, that CO2-rich atmosphere enabling in-situ fuel and oxygen production through already demonstrated chemistry, which may be the single most strategically valuable resource advantage on this entire list. Feeding a colony. A narrow edge to Mars, driven by its Earth-like day length and its free, abundant atmospheric CO2 as a direct agricultural input, though offset by the same dust storm power vulnerability that threatens nearly every other Martian system. Environment and temperature. Mars wins on thermal stability, avoiding the Moon's brutal 300-degree day-night extremes, but Mars introduces the unique, colony-threatening hazard of global dust storms that the Moon simply does not have to contend with. Habitat construction. Essentially a draw on technique, both leaning on regolith and lava tubes, but the Moon wins as the far safer place to actually develop and debug these technologies first, before betting them on a destination where mistakes take years to correct. Governance and ownership. Not a clean win for either side, but a nearer term, more urgent pressure point on the Moon, given active, current competition over a handful of prime polar resource sites, versus a more theoretical, longer horizon question of self-governance on Mars, communication and psychological isolation. Moon, decisively, and arguably the most underrated category in this entire debate, backed by real analog mission data from HIC, and Mars 500 showing measurable psychological strain under Mars realistic delay conditions, economics and near-term funding reality. Moon, decisively, reflected clearly in where every major national space agency has actually put its current, appropriated, non-speculative budget dollars. A global race, as it stands right now, overwhelmingly, Moon-focused across every government space agency on Earth, with Mars driven almost entirely by one private company's founder-stated ambitions rather than any funded national program with a hard near-term date attached. Added up honestly, category by category, and the Moon wins more individual categories. But, and this is the twist this video has been building toward, winning more categories doesn't necessarily mean winning the actual argument, because these categories are not all equally weighted, and more importantly, they're not actually in competition with each other the way this video's own title implies. Here's the uncomfortable truth that most space content on this platform refuses to say out loud. This was never really a fair fight, because Mars versus the Moon was all slightly false framing to begin with. The moon is not a competing final destination for permanent human civilization in the way Mars is envisioned to be. The moon is 3 days away, tidally locked with brutal thermal swings, has no atmosphere to work with for fuel production, and offers no serious long-term path to a genuinely self-sufficient, multi-generational, Earth-independent civilization. Its economic and scientific value lies overwhelmingly in what it teaches us and what it enables, not in what it ultimately becomes. Mars, by contrast, despite every one of its genuinely brutal, currently unsolved challenges, the isolation, the radiation, the dust storms, the 7-month transit, the unproven gravity biology, is the only other rocky body in our entire solar system with a plausible, if extremely difficult, path to something resembling genuine long-term self-sufficiency. An atmosphere thick enough to derive fuel and oxygen from, a day length of 24 hours and 37 minutes almost identical to Earth's, a gravity high enough to plausibly support long-term health, and enough accessible water, minerals, and land area to theoretically support a growing multi-generational population that doesn't need to constantly resupply from Earth. Also, the real answer, the one this video has been building toward the entire time, is this. It's not actually Mars versus the moon. It's the moon, then Mars. Every major serious space agency's actual roadmap already reflects exactly this sequencing, not because of some romantic notion of one giant leap at a time, but because the moon functions as the only place in the solar system where humanity can test, fail, fix, and retest the exact technologies a Mars colony will absolutely require: closed-loop life support, radiation shielding, ISRU resource extraction, autonomous construction, long-duration dust mitigation, and partial gravity human biology, all while remaining just 3 days from a rescue mission, rather than 7 months. Think of the moon as the ultimate dress rehearsal, the place where every single mistake is survivable, and Mars is the actual performance, the place where those same mistakes might not be. A colony that skips straight to Mars without ever solving these problems closer to home isn't being bold. It's gambling human lives on technology that has never been proven in a partial gravity, deep space environment, with no realistic way to correct course if something fundamental turns out to be wrong. This is why NASA explicitly frames Artemis using the phrase, "moon to Mars." It's why SpaceX, despite Elon Musk's public Mars ambitions and stated timelines, is also actively developing a lunar variant of Starship for NASA's Human Landing System program, testing much of the same core technology on the moon first. It's why China's lunar and Martian ambitions are sequenced the same way. Nobody's serious in this industry, once you look past the headlines and the social media hype, is actually proposing Mars first, moon never, or all proposing some version of exactly this sequence, because the engineering logic behind it is simply overwhelming once you walk through it category by category, the way we just did. So if the question is, which is the better place to build a colony? The honest answer, backed by every category we just walked through, isn't a single winner. It's a sequence. The moon is where we learn how to survive somewhere that isn't Earth. Mars is where we prove whether humanity can actually build a second home. What the next decade actually looks like. Let's get specific about what to actually watch for, because this isn't a debate that stays theoretical much longer. A remarkable amount of it is going to be settled, one way or another, by real missions with real hardware within the next several years, and knowing what to watch for will make every future plan about this topic make a lot more sense. On the lunar side, watch for the first crewed Artemis landing near the South Pole, which will be the first time human boots have touched the lunar surface since 1972. And unlike Apollo, this mission is explicitly targeting a permanently shadowed polar region specifically to begin serious water ice prospecting, not just flag planting and rock collection. Watch for the continued cadence of NASA's commercial lunar payload services missions, since these smaller, less publicized robotic landers are quietly doing an enormous amount of the actual groundwork, testing precision landing, testing resource detection instruments, and testing communication relay infrastructure that every future crewed mission will depend on. Watch for China's continued lunar sample return and eventual crewed lunar landing efforts, and pay close attention to how the coordination, or lack of coordination, between the Artemis Accords coalition and the separate China-Russia International Lunar Research Station coalition actually plays out once both groups have real hardware and real astronauts operating in the same general South Pole region at the same time, because that dynamic, more than any single scientific discovery, may end up shaping the actual pace of lunar development this decade. On the Mars side, watch for continued Starship test flights and specifically watch for whether SpaceX successfully demonstrates orbital propellant transfer, spacecraft to spacecraft refueling in orbit, because this single capability is an absolute prerequisite for any Mars mission using the current Starship architecture, given how much propellant a Mars-bound Starship needs compared to what it can carry directly from an Earth launch alone. Watch for whether NASA's restructured Mars Sample Return Program successfully brings back its collected Perseverance samples, since the scientific analysis of confirmed Martian rock and soil samples in Earth laboratories, rather than remote rover instrument readings alone, could meaningfully refine everything we currently believe about Martian water distribution, soil chemistry, and even the tantalizing, still entirely unresolved question of whether Mars ever hosted microbial life. Watch closely for whatever the first uncrewed Starship Mars landing attempt actually reveals, because a real landing attempt, successful or not, will generate more genuine engineering data about Mars entry, descent, and landing at this vehicle scale than every previous Mars mission in history combined, given how dramatically larger and heavier our Starship is than any previous Mars lander. It's also worth watching the partial gravity research question specifically, since this remains, as we discussed back in Chapter 2, one of the biggest genuinely open scientific gaps in this entire debate. Proposed concepts for centrifuge-based partial gravity research facilities, whether in low Earth orbit or eventually on the lunar surface itself, have been said within the space research community for years, and any serious near-term progress on actually building and operating one of these facilities would be one of the most quietly important developments in this entire field, because it's one of the only realistic ways to generate real data on this question without simply sending human colonists to live under partial gravity for years, observing what happens to them as the experiment itself, which is obviously the approach nobody wants to be forced into by default. If you've made it this far, you now understand this question at a level that most space content on this platform never even attempts to reach. Not vibes, not hype, actual numbers, the actual constraints, and the actual reason why the world's space agencies and companies are sequencing this the way they are. Let's do one final, honest recap of the shape of the argument, because it's genuinely counterintuitive, and it's worth hearing it laid out plainly one more time before you go. This video is not a "the moon is better than Mars" video, and it's not a "Mars is better than the moon" video either, even though we spent 13 chapters walking through category after category where one destination or the other came out ahead. The actual conclusion is that the question in the title is, itself, subtly the wrong question, because these two worlds were never actually in competition with each other in the way versus implies. One of them is a proving ground. The other one is the destination the proving ground exists to serve. Treating them as rivals competing for a single spot in humanity's future is exactly the framing that most online space debates get stuck on, endlessly, without ever resolving anything. Because both sides are technically right about their own destination's strengths, and both sides are talking past the actual sequencing question that resolves the whole debate the moment you take it seriously. The next decade is going to answer questions that have been theoretical for 50 years. Artemis astronauts are going to walk on the lunar South Pole and start extracting real water ice for the first time in human history. NASA and private companies are going to test closed-loop life support systems in genuine lunar conditions, not simulations. And somewhere in the coming years, depending on who you believe, the first uncrewed Starship missions are going to attempt to land on Mars and start testing whether everything we've theorized about in situ fuel production actually works when there's no room for error and no quick fix from Earth. We are, genuinely, living through the opening chapter of humanity, becoming a multi-planetary species, or at least attempting to. Whether that attempt succeeds is nowhere close to guaranteed. Every single category in this video, gravity, radiation, isolation, economics, agriculture, governance, contains real, unresolved, currently unanswerable questions. And it would be dishonest to end this video pretending otherwise just for a satisfying conclusion. But the fact that we're seriously trying, with real hardware, real budgets, and real engineering, rather than just talking about it in science fiction, is something worth paying close attention to, and something worth understanding properly, rather than through the flattened, oversimplified version of this debate that usually shows up in your feed. If this video helped you actually understand this debate instead of just picking a side because Mars looks cooler in movies, let me know in the comments which destination you think humanity should prioritize and why. I read every single one. And some of the best follow-up video ideas on this channel have come directly from comment section arguments just like the one this video is about to start. Subscribe if you want to be here for the next chapter of this story, as it actually unfolds in real time over the coming years. And I'll see you in the next one.